Swayam Prabha. Digital India. Educated India.
Welcome to the fourth lecture of module 2. In this lecture, today we shall discuss about the toolpath planning. So, the content of this lecture is highlighted on this slide. We shall first discuss about briefly what is toolpath planning, and then we shall discuss various area filling methods such as grid cutting, pixels, mask, raster, direction, contour, spiral, matte, hybrid, continuous and topology optimized area filling methods. So, as discussed earlier, for the researchers those are working in CAPP of additive manufacturing, they need to perform the operations particularly for two particular field. One is slicing, another is toolpath planning. So, to convert the 3D data or the 3D CAD data into the G codes compatible for the additive manufacturing machine, we need to perform the slicing, which we have already discussed in our last lecture, and another is toolpath planning. So, toolpath planning is basically a critical step of computer aided process planning for additive manufacturing. It influences its surface roughness, dimensional accuracy and part strength after completion. Toolpath mainly includes the three types. So, there are total three different types of toolpaths. One corresponding to the scanning of the outer contours, the scanning of the inner contours and scanning the inside area, that is sometimes called as area filling. As you can see, this is the outer boundary of a particular slice. This particular slice shows here the inner boundary, and after that we know that there will be material here and there will be no material here. Therefore, the question comes, how should we add the material in this zone? The method of adding the material in the required zone is called as area filling method or area filling path. So, area filling path is basically what you are seeing here in blue color. This is a particular kind of path. There are different paths we are going to discuss today. As we have seen in our last lecture, the outer contours is consisted of nothing but the collection of lines. Therefore, you know the point and you know the next point on the contour. Those you can easily obtain by obtaining the intersection between the horizontal slice and the STL file. Therefore, you can easily generate the G code as well, because you know the point on which the currently tool is and you also know the next point on which the tool has to reach now. Therefore, the question only comes here, what kind of interpolation is required, and as it is nothing but the lines, the linear interpolation is sufficient. However, if you are dealing with the slicing of accurate CAD models, that is also called as direct slicing, then in that case other type of interpolation may be required. So, therefore, in today's lecture we shall not discuss much about the scanning on the outer or inner contours, because this is very straightforward thing. We shall discuss more about the area filling paths, how to fill this area. So, there are different ways of filling the area in a slicing contour. As you can see on this slide, we may fill the area on a 2D surface or we may fill the area on a 3D surface. The different methods of filling the area could be grid cutting, pixel, mask and a path. So, in some additive manufacturing processes such as laminated object manufacturing, the raw material is in the form of sheets. Two sheets are joined together with the help of thermal or pressure activated glue, and a cutting operation is performed to separate the unwanted area from the part. In that case, the area filling is not exactly required to fill the inside area. However, it is required to remove the unnecessary material. So, for example, you are dealing with a process called loam and you are using raw material in the form of paper sheets. Now, you have also obtained the contour data through slicing. As this sheet is joined with another sheet on the bottom side, we need to now only separate out the unwanted region. We know that if we cut the path along with the contour obtained through the slicing, then this region where the material is will be separated out, and this region where there is no material will be separated out. Now the question is how to remove this portion also after completion of the part. For that, a grid cutting is performed. So basically, area filling in the case of laminated object manufacturing is quite different. We do not fill the area inside the slice. Instead, we fill the area which is not the part or which is not associated with the part. And how do we do that? We usually perform a grid cutting operation. Grid cutting is nothing but the combination of X passes and Y passes. And of course, these passes are associated with the cutting operation such as laser or knife. After completion of these grids, we can easily observe that it will be very easy that the user can easily remove these grids later on, so that we can get the outer periphery corresponding to the desired object. And in a similar fashion, after completion of the object, this portion can also be removed. If we do not perform this grid cutting, you can see it will be difficult to obtain this part out or to get this region out from the cube we produce or cuboid we produce through the process. Next is pixel. In the DLP based wet photopolymerization process, binder jetting process and material jetting process, the method used to scan the area inside the slicing contours is performed by scanning the pixels. As you can see here, in the case of DLP based wet photopolymerization process, light is projected and it is projected only on the desired region. In the case of binder jetting, the material is injected only on the desired region, and in a similar fashion, the material is jetted on the desired region. So now let us consider this particular domain. It is a rectangular domain which is consisted of lot of pixels. Let us assume that we are dealing with DLP based wet photopolymerization. In this case, what will happen? A light will be projected on the entire mirror, which will be consisted of lot of mirrors arranged in pixels. Now only those pixels will be activated, those are associated or falls inside the boundary we scanned through the slicing method. So as you can see, this boundary we have obtained through slicing, and the pixel those are falling inside this boundary are getting activated. As it is an internal contour, the pixels falling outside this boundary are getting activated, and light will be projected on the photopolymeric material only in this region. Therefore, as a result, you will get this type of object. Of course, you can see the material curing or addition accuracy is governed by the resolution of the pixels that we are using in the process. If the pixels are more, then of course your geometry will be more accurate. If the pixels are less, obviously your geometry will be less accurate. You can consider the analogy of your 2D printing. It is exactly same. For example, you are printing an image using the 2D printer and you are utilizing less DPI, means less number of dot per inch, the resolution will be bad. And if you are using high DPI, then of course your quality of the image which you are printing will be better. Now let me consider another case of binder jetting. In the binder jetting also, we have a head which is consisted of several nozzles arranged in an array. Only those nozzles get activated which are required. So if I have a long nozzle of this much size, when it will reach at this location, no nozzle will be activated, and when it will reach at this position, these pixels will get activated in the nozzle correspondingly, and material will injected here. As it will move further, different nozzles will get activated and inject the material or inject the binder on the sheet. Like I said, in a similar fashion it happens in the material jetting. So filling the area inside the contours we obtained through slicing is quite easy in the case of material jetting, binder jetting and DLP based wet photopolymerization. It governs by the method of pixels. Also, in some wet photopolymerization process, a mask is used. So if we have a floodlight and the floodlight is falling on a glass, then the entire light will pass through it. If I am using now some mask and not allowing some of the light to pass through the glass, then the light will pass only through the transparent region. This type of method we can extend for scanning each and every layer in some of the wet photopolymerization process. So what happens? We start with a glass with no mask like here. Assume that the boundary you are seeing here in pink color is associated with the boundary of the glass and the entire region is transparent. If the light will fall onto it, the light will pass through everywhere. Now if we want to scan the area or we want to cure the material inside this region, then we have to make the opaque region opposite of it. So this region will become opaque in this case. Now if the light will fall onto this glass, then of course it will pass through this transparent region, and hence as the light will pass through this transparent region, as a result on the build platform this area will get cured. So in summary, the area filling here is created by creating the negative of it on the glass or on the photomask. Then after that, the entire layer is scanned in a single go. You need not to scan like we discussed in last case pixel by pixel here. The entire region can be scanned in a single go. However, the three methods we discussed are applicable for either wet photopolymerization or material jetting or binder jetting. Other additive manufacturing processes uses the method of area filling called as path. What happens? So if we talk about FDM process, the material is extruded from a nozzle and there is a build platform. The build platform moves relative to the nozzle and capture the droplets or the molten material falling onto it appropriately. Now when filling the area which is inside the boundary or which is associated with the part has to be traced by a particular path. There could be different types of path. On that we can scan and fill the inside area. Let us first discuss about some of the important requirements from a path or expectation from a scanning path or area filling path. Then we shall move ahead our discussion towards the different types of area filling strategies based on toolpath. So the first one is the toolpath should be in such a way that it can quickly dissipate the heat from the slice. In some additive manufacturing processes, the material is added through melting the raw material and depositing on the substrate. This causes the workpiece to heat up and wrap due to thermal expansion. Therefore, care is to be taken during depositing to ensure that the distortion is at a minimum. Therefore, the area filling strategy used should be able to dissipate heat quickly and prevent accumulation of heat in any region of the slice. Also, the toolpath should be in such a way that it should have minimum number of lifts. Lifts means number of switch off and on. As you know that most of these additive manufacturing processes are inertia based, means some mass transfer is taking place. We know that when the process starts or stops, in this transition phase, the deposition of the material is not stable. Let me take an example of wire arc additive manufacturing. If we are adding material by welding process, when the arc starts, the deposition of the material is either more or less. And in a similar fashion, when arc stops, the deposition is either less or more. In between, it is quite consistent. Therefore, we should avoid the number of switch off and on those used to get performed while scanning an area. The third property of an ideal tool path, it should give us a constant machine feed rate. For example, if you are dealing with a tool path which is consisted of a lot of turns, then in that case, the relative speed between the deposition head and the substrate may not remain consistent. As a result, if the speed is not consistent, at some portion the material will get deposited high and at some portion less material will get deposited. In that case, you will end up with uneven layer. Therefore, your tool path should be in such a way that you get nearly uniform feed rate throughout the process. Fourth and the most important one is constant step over. The step over value should be constant in a slice. What is step over? Step over is nothing but the distance between the two consecutive passes in a XY plane. So for example, if we are filling the area inside this rectangular slice and this is the first pass. Now the next pass will be at a distance. The distance between the two consecutive passes in this XY plane will be nothing but step over. So your area filling strategy should be in such a way that all the passes are at the constant distance. It should not happen that some passes are close and some passes are far away. If we will do that, we will end up with having an uneven layer. Now let us see the different area filling tool paths. The first one and the most efficient one is the raster. Raster path pattern is a simple, efficient and robust to cope with any boundary. However, the build accuracy is quite poor in the layer. As you can see this diagram, here you are seeing X raster scanning paths. Why we are calling it as X raster? Because the scanning passes are along the X axis. This red color path, it is showing the tool is moving in air. Means the tool is going from this point 1 to 2, depositing the material, and then it gets switched off here, lifted up, then goes to a new position at this location 3 and then deposit from 3 to 4. Of course, these red passes, like I said, are the movement of the tool in the air. If it is Y raster, then of course we will deposit the material along the Y direction. Here also again you can see the tool is moving from point 1 to point 2 in the Y direction, like here, and it will add the material, and then the tool will get lifted and it will move from point 2 to point 3 here, and then it will start adding the material along this line and it will reach to point 4. Again it will lift and come back to next position, that could be 5. Similar fashion it will add the material, then again it will come back like this, it will come back like this. These dotted lines are showing the movement of the tool in the air when it is not adding any material. So this is the Y raster scanning. In some cases, we also do the XY raster scanning when the tool path are given in X direction as well as in Y direction. So why we do this? This is because to get the homogeneity in the deposited material property. For example, if you are adding material along the X axis, the strength of the part in this direction will be different as compared to the strength of the part in this direction. In a similar fashion, it will happen here as well. the strength will be quite similar in this case in both the directions. That is why XY raster scanning or a combo of the two raster scanning is preferred for a layer. The next very popular area filling method is zigzag. Zigzag is put forward to connect separate parallel lines into a single continuous pass, leading to less build time with fewer transition motions. As you can see in this diagram, the toolpath starts adding material from this point onwards. It follows just the x-axis, for example, just very similar like we discussed in x-axis raster or x raster. But in the end, the tool doesn't lift. Instead, it remains on the slice itself and keep adding the material, reaches to the next line and add the material. So what is happening here, you can see these edges or the boundary of the contour are approximated by linear edge or like this. However, due to the discretization error on any edge which is not parallel to the tool motion direction, the outline is poor, leading to poor surface quality of the printed part. This particular strategy, the zigzag, is also called as direction parallel strategy. The direction parallel strategy is the most commonly used toolpath in additive manufacturing machines. However, it used along with the combination of contour parallel toolpath, and hence the entire toolpath is called as hybrid toolpath. That we will see after some time. It is also possible that we scan the layer. For example, this is the first layer and we are scanning it in x direction. So the long passes are, you can see, are in x direction. Now if I want to scan, for example, the next slice looks something like this, and it is possible that we scan the inside area at an angle from x-axis. So for example, this is the x-axis and we are going to scan at 45 degree. So the tool path will look something like this. Now you can see the tool path is at 45 degree. Now the next layer can be deposited at another angle, maybe 90 degree from x-axis. Hence the tool path will be something like this. So the point is, if we deposit the material with different angles at different layers, you will get the homogeneity in your part. Because as we already discussed, if we just deposit the material like this, the strength of the part in this direction, for example, this is sigma 1, and the strength of the part in another direction, that is sigma 2, are quite different. While if we just use the combination, in like first layer we have scanned by 0 degree angle, then second at 45 degree, then next at 90 degree, then next again at 0 degree. Like this, if we will keep on doing, then the final part we will obtain will be quite homogeneous. The next commonly used tool path for additive manufacturing is contour parallel tool path or contour path. The contour path is applied by offsetting the contour of the geometry. Already these contours you have obtained by the slicing between the horizontal plane and the STL file. These contour paths create a series of offset starting at the outer boundary and progressing towards the center, like you are seeing in this image. All the closed loop contours, if you see, are all together. They are collected like offsetting towards a particular direction. The toolpath has to be restricted in the area defined by the boundaries of the cross section, and hence it is called as contour parallel or modal offset also. What you are seeing here, this green color boundary, it is getting offsetted by a finite value, and each time it moves towards the inside boundary. If there is any internal boundary also, then we need to take the interpolation with that as well. This is a very simple example of contour parallel toolpath. The one here you are seeing is another example of contour parallel toolpath, and the thing I want to highlight here is some advantages and disadvantages of this tool path. Like, the feed rate will remain quite consistent while depositing on these tool paths. However, one can notice that some voids will remain while deposited by these tool paths. However, if we use a combination of this tool path with zigzag, then we may get some better results. Other tool path is called as spiral tool path. The spiral tool path is widely used in numerically controlled machine, while it is only suitable for a specific geometry model in additive manufacturing. This is very simple example of a spiral, but this is for scanning a circular region. You can see it is very easy to generate such tool paths for simple geometries. But if the geometry is slightly complicated, like you are seeing here, this is an internal boundary and this is an external boundary. There will be material here and there will be no material here. If we use the spiral tool path for this, the results is shown here. The issue with this tool path is there may be some portion where the step over is not consistent. The step over is same here, while it may not remain same at some particular locations. Therefore, the property which we discussed, like the tool path should be in such a way that it maintains the constant step over, getting violated here. But this tool path gives another benefit to us, that is a consistent feed rate, because the tool when moves on such tool paths doesn't change its feed rate very often, and hence the deposited material at each location remain consistent. Other nowadays getting popular tool paths for additive manufacturing are space filling paths. The space filling curve based tool paths uses continuous curves such as Hilbert, piano, E-curve, etc. to fill the cross section in a layer. Example of the space filling curve Hilbert based tool path of a layer is shown in this figure. So this is a typical Hilbert tool path. This is its first iteration, this is its second iteration, this is third and this is fourth. This type of tool paths are very nicely follow the four requirement we discussed. Let us see here, number of switch off and on are very less. Also you can see the step over is everywhere maintained. Everywhere if you measure the distance between the two consecutive passes, anywhere it will remain same. But the issue with these tool paths is that they are not capable of obtaining any random geometry. Another benefit of these tool paths is they can dissipate the heat nicely when they deposit on a layer. But the only problem with this tool path is they are not very easily available for accommodating any geometry. Like the Hilbert tool path is only suitable for rectangular geometries, that too of a specific size. Let us see how we can use Hilbert tool path for generating the area filling path for a random geometry. Like you are seeing here, this pink color geometry is showing the boundary of the object which we obtained from the slicing, and this is the space filling curve available for a particular step over for having a larger size from this scan boundary. Now what we can do, we can perform a trimming operation. We just remove the points those are falling outside this contour, and as a result you will have the tool path like this. Now you can see it is having a constant step over. It is also dissipating the heat as per the requirement. The feed rate also may remain constant throughout. The only difficulty now we are facing here is lot of number of switch off and on. This type of issues can be easily resolved by connecting these segments together in such a way that we can optimize the number of switch off and on. Now let us discuss about the another very popular additive manufacturing tool path, particularly for directed energy deposition based process and called as MAT. MAT stands for median axis transformation. So the traditional path like contour parallel are not really adequate to cover the geometries of part and may leave some voids or gaps like we have already seen. As you can see here, we discussed, we were trying to scan the area inside this particular boundary and we end up having some voids into it if we use the contour parallel or contour path. But if we use the matte tool path, you can see the deposited tool path is very consistent and the distance between the two passes are always constant to the step over value. The only issue what we are facing here is number of lift, because all these passes are having some segments. So for example, if I talk about this line, it is starting from here and ending here, and similarly this line will start from here and it will end here. Means it will start depositing material here and then it will pause or stop and it will change its position and start depositing on another location. Of course, it can be optimized up to a certain amount by connecting the nearby passes in such a way that we have the minimum number of lifts. However, it cannot be eliminated, some lifts may be there. So what is matte? How these tool paths are generated can be seen here. If the contour depicts the geometry of the boundary, then the matte is shown in this figure. This orange color line is nothing but the matte of this particular contour. It is also known as skeleton, describing the domain shape based on the median axis bisecting the domain into two halves. To get the skeleton, the algorithm corresponding to matte is used, which is easily available with many open sources as well. In this case, we used to generate the circle, those are the maximum possible circle, and remain the tangent on the nearby boundary points, and we keep on doing it and collect the points, those are nothing but the center of these circles, and hence we get the median axis. Then after that, we keep on offsetting this median axis by the certain amount of step over. As a result, you get nothing but the tool path corresponding to matte. The tool path which goes outside this boundary is simply trimmed off. And finally, you will have the tool path corresponding to matte. Due to its unique benefits of having the constant step over and feed rate throughout, these tool paths, like I said, are very popular nowadays for directed energy deposition. Finally, if we use a combination of a tool path like zigzag with contour parallel or matte with zigzag or fractal with contour parallel, we will have some unique benefits, and this type of tool paths are called as hybrid path. So basically, the hybrid path planning strategy means the combination of different approaches to obtain various advantages. For example, you are seeing here, as we know, when we scan by the raster path, the issue comes along with its edges. It approximates any contour by linear edges. Therefore, the outer profile will not remain as good as we required. So what we can do, we can deposit few lines from outer by utilizing the contour parallel, and the inside we can fill by the zigzag area filling. However, if I use all the time contour parallel, we know that it may leave some cavities behind. So a combination of zigzag as well as the contour parallel giving us the best option. In a similar fashion, you can use the combination of any two tool path to obtain the hybrid path. So far, what we have discussed, the tool paths were having at least some finite number of lifts. There were some attempts made in which we can obtain the tool path, those are continuous in nature. Like I already discussed, during the start and stop of the material deposition on a substrate, the process is unstable. To prevent this, the number of times the process switched off and on in a slice should be minimized. And if we have a continuous path, it can fill the entire slice area in a single continuous path from starting to finish, and hence we will have only switch on and off once. Such an example is shown here. This is a continuous direction parallel toolpath. This is typically optimization problem which is solved to eliminate the number of lifts. Here you can see this is the outer geometry approximately I am drawing, which is scanned by the direction parallel path, but it is continuous in nature. Now we are not having any switch off and on, and therefore the tool path is continuously depositing the material. This is an example of continuous hybrid tool path. Hybrid, why hybrid? Because the outer contours are deposited by contour parallel and the inside is deposited by raster or direction parallel. As a result, you will have the benefit of now three things. The outer geometry is deposited in a better way. Here you can see the edge is approximated by the linear curves, while here the edges can be even approximated by non-linear curves, and hence the exterior will be very smooth in this case. Also, there are no switch off and on. Also, some attempts nowadays are made towards generating the continuous tool path which is based on fractal like tool path. What you are seeing here is the map of India. It's a very complicated geometry. It is scanned through a single line. It is a single line. The tool starts from here and ends here, and it doesn't get switched off anywhere. Also at the same time, the step over is maintained throughout. So this was the continuous tool path for generating the area filling strategies. However, in some cases, we really do not want 100% inside area filling. Means we need some hollowness inside, or we need to deposit less material inside, and hence we can save the material as well as we can save time. To deposit the material with less density in the inside contours, the strategies are slightly different. So some of the strategies available in the open source Ultimaker Quora are highlighted here. These strategies are used to fill the interior with less density. Of course, you can use these strategies to fill the 100% density as well, but they are more popular to deposit the material with less density. So for example, you see this, there are some voids here, because intentionally we want to keep these voids so that we can get the lightweight structures. These are some printed part by utilizing some of these strategies through FDM. As you can see here, these are some hollow, different strategies for creating the hollow structures inside. Another very popular strategy to create the low density or the topology optimized structure inside is honeycomb structure. As you can see here, it deposits the material along the lines of a hexagon, and it keeps on doing it to build the entire part. There is no material here, only the material is added along these edges. If the size of this polygon is less, then of course the density of the material or the density of the slice will be more. So far our discussion was limited towards the scanning strategies for 2D surfaces. However, nowadays the processes like FDM, DED are used along with the robotic arm, and we are capable of realizing the objects along with 3D slicing. In that case, the material has to be also deposited on the curved surfaces. For example, if I want to add the material on a cylindrical surface, or I want to create a feature along with a cylindrical surface, in that case the layer will not be 2D, it will be a 3D structure. The popular area filling strategies for such cases are shown here. There are three main types of area filling methods in free-form surfaces. For reference, the direction parallel, the contour parallel, and sometimes the space filling. However, not many tool paths are easily available for adding the material on the curved surface. Usually we take the help of the existing CAM packages and extract the strategies those are associated for finishing or the machining strategies to get the G codes, and then we add the material along these tool paths instead of removing it. So with this, thank you very much.